Hi everyone, we're just going to go through a few examples here on the fundamental theorem of calculus, a very grandiose sounding theorem here. So if you've watched the previous video, you'll get the idea that what we're talking about here is definite integration. So when we do the integral between b and a of a certain function with respect to x, we say that that is big F of b minus big F of a, where this function here, f of x, is the antiderivative of f of x. Or we could say f dash x is equal to f of x. Okay, so this function here that we're substituting the numbers b and a into is an antiderivative of f of x, and we know how to do the integration here. And of course we know what we're talking about here is working out the area underneath this function f of x. So this is y equals f of x between b and a. Now, another derivation of the fundamental theorem that flows from this is if we kind of do the reverse process. If we do the derivative of the integral, we know we're going to get back our original function. So it looks something like this. If we do the derivative of, I'll call this a function of t, let's say f of t dt, we know that when we undo this thing here is going to be a function of x, and then when we do the derivative it's going to undo this integration process. So what we end up with when we do this is just f of x. Okay, so that's another way of looking at the fundamental theorem of calculus, the idea of this relationship between integration and differentiation. And these few examples I'm going to do show how that works. Okay, so looking at this one here, you can see we're just doing the derivative with respect to x of all of this stuff here. So we really don't need to know how to do this. I mean, you could do it if you wanted to, but it's really just going to be a lot quicker to understand that this is the fundamental theorem, and the answer to this question is just going to be 1 plus x squared over 2. No plus c, because when we do the derivative, the plus c is going to drop out. So that's it, 1 plus x squared over 2. Done. If you wanted to do the full method, you could integrate that thing. You've got the integral from x to 0. I'll just do this once. A half plus a half t squared dt. So you could say that that's, remember we're doing with respect to the variable t here, half t plus a half t cubed over 3 plus c, and this is going between x and 0. So really we've got t over 2 plus t cubed over 6 between x and 0. I'm only going to do this craziness once. So we've got x over 2 plus x cubed over 6, and then minus, substitute 0 in there, you can see that we're going to get 0. Okay, so that's the integral, and then we're going to do the derivative with respect to x. So let's do the derivative with respect to x of this thing now. And what will that look like? We're going to get x over 2 becomes a half. Okay, so we've got a half there. The derivative of x cubed over 6 is going to be 3x squared over 6, so that's just going to be a half x squared, and that is exactly what we had before, 1 plus x squared over 2. Okay, so save yourself the time, recognize the fundamental theorem, save yourself lots of time. Here's example 2, integrate that with respect to x. Again, trying to understand that integral or anti-differentiation and differentiation. So let's do this the long way. The derivative of this is 3x squared plus 5. And then we're going to integrate that thing there with respect to x. Okay, so 3x cubed over 3, x cubed. The integral of 5 is just 5x, and then plus c. So remembering though that we're not going to need the plus c here, so the integral of the derivative is just going to be x cubed plus 5x. So again, we don't need to have this minus 1 here. That's going to disappear. So I'm going to just say that the answer is x cubed plus 5x. Last question here, this is a good one. again, just understanding the area ideas here. So we've got a function from 0 to 10, not a specifically defined function, and we want to determine a few areas, really C and D, and what I'm really interested in. The answer to A, f of 2, is going to be, what's the value of the function at x equals 2, and that, of course, is 4. The value of the function at 7 is, there at minus 1. C says, what's the integral from 4 to 0 of this function? So that is this area here. So we can work that out pretty easily. I mean, even if we were like counting squares or something like that, I can just count the squares under there and see, well, there's basically two triangles, isn't it? Well, it's one big triangle. So the base is 6, the height, so the base is 6 along here, the height is 4. Oh, sorry, not that one. We've got to do from 4 to 0, sorry, not all the way across, so it's a little bit trickier. From 4 to 0. So we could do it by going this triangle plus this trapezium here. So we've got a half times 2 times 4 is the area of the triangle. And the area of that trapezium over there is a plus b over 2 times the height. So in this case, the a is 4, the b is 2, times the height between them is 2. So that's the formula we're using for area of the trapezium. So this is 4 plus 8 over 2, 4. So this is 4, 6 over 2 is 3 times 2 is 6. So that area there is 10. We could count the squares in this case, it's pretty easy. And the last one there says, what's the integral from 10 to 2? Okay, let's check that out. The area from 10 to 2. Okay. So that is this bit here and this bit here. Now remember, if I ask the question, what's the area under the curve, this is going to be a different question. All this is saying is what's the integral from 10 to 2 of this function. So what we need to understand is that this will count as negative and this area here will count as positive. So the positive bit is just a half. The base here is 4 long and the height is 4. So that area there is 8. And this bit here, which is the negative part, gosh, we could almost count squares here because this is nice. 1, 2, 3, 4, 5, 6. I think I can count 6 there. So minus 6. So this is going to be 8 minus 6, which is 2. So the integral, if you were to do that, would spit out a value of 2. Remember, that is not what is the area between the curve, or in this case the lines and the x-axis. If we're going to do that, the answer would be 8 plus 6, 14. In this case, if we just did the integral, we get a value of 2.